Great, thanks, Lance, and welcome everybody. Thanks for being here today. We're going to talk about today is optical networking demystified. As we were chatting a little bit before the broadcast here, these are very interesting times around the world with COVID, and really generating the demand for bandwidth, probably really like we've never seen before. So as we talk a lot with our rural carrier customers, smaller carrier customers, a lot of those folks have been getting by with SONET networks, for example, or SDH networks in other parts of the world, or even carrier Ethernet networks. And what we're starting to see is there's just so much demand for bandwidth right now that those networks are just going to be out of gas, and they sort of have to move to another technology, a technology of optical networking. But sometimes the problem is if you've never deployed an optical network before, you may not know what the terms are and the vocabulary and the different types of things you need to be looking for. So that's really what today's webinar is all about, is demystifying all that for folks. We won't run you, mercifully, we will not run you through a full list of products. We're just going to talk about terminology, so this is going to be educational for everyone. Just a quick word about who Ribbon is for IP and Optical. Ribbon is kind of a new name in the world of IP and Optical, but in March of this year, Ribbon acquired a company called ECI Telecom. ECI is a long-time provider of Ethernet, IP, and optical equipment actually around the world. So we have a full line of optical Ethernet and IP platforms, everything from little bitty pizza boxes to great big multi-terabit full rack systems and management to go with it. And we focus on a range of different types of customers, from service providers to electric utilities. We help them build residential broadband backhaul networks. We help them build mobile broadband backhaul networks, wavelength services and optical networks, and we also do carrier Ethernet networks. One of the things that's interesting about our portfolio is we have a lot of big carrier capabilities, very full-featured, sophisticated types of capabilities, yet easy to use, and they come in small carrier kind of bite-sized packages. So we think we enjoy serving carriers in the rural space, and that's who we are. Tell you what, we're going to have a little bit of contest here, and Lance, do you want to start us up?
Sure, yeah. When we started talking about this webinar today, I was thinking, man, what is DWDM again? It was sort of tough. So I'll tell you what, the first person who can tell us what DWDM stands for and type that in the Ask a Question box that we mentioned, or in the chat area, either or, the first person to do that will send you a Ribbon-branded JBL Flip 5 Bluetooth speaker. Very nice prize. So I just want to get the interaction going. So type away and see who can respond to that. Again, DWDM, what does it stand for?
Okay, sounds great. So as we get going today, just a reminder, no one's dumb, just folks are unfamiliar with things, right? So we're going to talk about what can optical networks do for me, what kind of problems do they solve, what are the major piece parts, what's the vocabulary I need to know, what do I have to think about when I deploy a system, and a little bit of, is there any cool stuff on the market that I ought to be aware of? So let's jump right in here. What can an optical network really do for me? There are a couple of very fundamental networking problems that really only optical networking does very well. And the first thing is to increase capacity without deploying more fiber. If you're trying to connect sites A and site B and you're out of fiber, deploying more fiber is a real pain. With DWDM, or optical networking equipment, you can increase that capacity without more fiber. You can go all the way up to greater than 10 terabits of capacity on a single fiber pair. That technology is available. The second thing that an optical network can do for you is you can actually increase distance without deploying a lot of electronics. If site A and site B are very far apart, and all you have is a SONET network or an Ethernet network, you would actually have to cascade multiple pieces of electronics to sort of regenerate or repeat that signal, and that's very, very expensive. Optical networking is uniquely cost-effective in allowing you to transport over distance without deploying lots of electronics. So only optical does those two things, and that's what's driving people who have never bought optical before to do it now. Optical does a few other things in sort of uniquely valuable ways. It actually can protect the traffic in uniquely valuable ways. It can encrypt the traffic in ways that IP and Ethernet cannot, and it can actually allow you to rearrange your traffic in ways that other protocols sometimes struggle with. So fundamentally, only optical will solve your capacity and distance challenge you need in these kind of crazy times. So one short physics-like lesson, just a couple of basics when we talk about optical. It's light, okay, and light exists as electromagnetic waves, and you can see a picture. It actually has a wavelength. So different colors of light have different wavelengths. So you'll hear folks talk a lot about this wavelength or that wave, and the wavelengths have a distance that is measured in nanometers or a billionth of a meter. So you'll hear people very often talk in terms of nanometers. So if you look at the electromagnetic spectrum in the upper right-hand corner of the slide here, light that you can actually see with your eyes is in kind of the 300 to 700 nanometer window. That's called the visible spectrum. And there's light that's used for what are called gray optics. We'll talk about that. That is in the 1310 nanometer window. That's in the infrared region. You can't see it, so if you get an optical fiber and you don't see anything coming out the end, that doesn't mean there isn't anything. Don't hold it up to your eye. And then the window where it's kind of the 1500 nanometer window, that's used for what are called wavelength division multiplexed or WDM wavelengths in an optical system. The reason why folks chose 1310 and 1550 as kind of wavelength bands for telecommunications optics is shown in this curve on the lower right. You're transmitting light down optical fiber, which is a piece of glass. That piece of glass is really, really abnormally clear. If you had a giant block of it, you could just see right through it for miles. It's just amazingly clear. It's not like a window, but it does have loss associated with it, and that loss varies depending upon the wavelength of light that's going down the fiber. So you see this kind of loss as a function of wavelength curve, and you see at 1.3 microns or 1300 nanometers, you see it's kind of a low loss portion or low attenuation portion of the spectrum, and then you see kind of another low loss portion around that 1550 window. So again, 1310 is for gray optics, 1550 is for colored optics, and then that's the physics lesson for today. Again, let us know if you have any questions. Bruno will be happy to answer them to them while I gab. So now that we've had our physics lessons, let's talk about the sort of the key pieces or components of an optical networking system. You can really think of it as three different types of things. First of all, there's an optical line system that operates at what folks call layer 0 sometimes. It is completely photonic or optical, and it deals with colors of light or wavelengths of light. It knows nothing at all about bits. It's just light. It doesn't know bits at all. And that optical line system allows you to manipulate wavelengths or optical channels, and it solves, that's the component of the system that really solves this capacity and distance challenge that we started off with. And guess what? It is not digital because it's not dealing with bits. It's analog. And there's some serious implications for that we'll talk about later. The second piece of an optical system I kind of lump these together. This is kind of the electronic part. Transponders, muxponders, OTN switches, those things are considered optical even though they're fundamentally electronic, and they do understand bits, and they create wavelengths. So in other words, if you look at the picture on the right, you see that blue area where you have OTN-based transponders, muxponders, switches at layer 1. They'll take in what's called a client over a gray optic interface at 1310 nanometer, and they will multiplex or groom or not lower speed traffic into a wavelength, which is kind of that red starburst there on the high side of the blue area. And that wavelength then feeds the line system, and the transponders, muxponders, and OTN switches are not analog, thankfully. They are digital. And then finally, there's a management system that ties the whole thing together. So maybe one more important thing, if you look at the picture on the right-hand side, the client there, that operates at 1310. That's between the transponders, muxponders, and switches, and the routers there on the very bottom of the drawing. Those are 1310 nanometers. They're not really called wavelengths, and they can't generally be combined with other singles onto a fiber pair. So you have to convert it to a wavelength, and it generally can't be amplified for distance very far. So if your problem is distance and capacity, you have to take that client optic, turn it into a wavelength, and then that wavelength is handed to the line system where it can be combined with other wavelengths and can be amplified for long distances. So those are the three portions of the system to remember. So let's dive into a little bit in some of the details of these types of systems. That basically forms the outline for the rest of the presentation today. First of all, we'll talk about what is a transponder. You'll hear this term all the time. Transponder is shown in the picture on the right there, has a single, exactly one client port and a single wavelength port, and the rate of the client and the network ports are roughly the same, and you don't do any grooming electronically. The transponder basically serves three functions. It terminates the client as it comes from the Ethernet switch or router or whatever the client is, and then it transparently wraps that client signal into something called an OTN frame, which is electronic. And that's kind of blown up in the picture on the far right there. You see a 10 gigabit Ethernet client coming in. It gets wrapped inside an OTN frame, and that OTN frame runs at a rate that's known as ODU2. We'll talk more about that in a little bit. And then it wraps around something called forward error correction. That's you'll see the acronym FEC, and that helps it go a long distance. And the important thing about the wrapping there is it doesn't touch the Ethernet VLANs or the IP packets. It just takes the whole shoot and match from the 10 gig client, puts it into an OTN frame, and off it goes. And it allows you to pick which wavelength you want that client to be mapped to. And you just provision that. You say, I'm going to pick this wavelength 1, wavelength 2, wavelength 3, or whatever. And that wavelength you create is now ready to join its other wavelength friends and be multiplexed together and transmitted over distance on the line system. Okay, let's keep going. What is it then a muxponder? So a muxponder is short for multiplexing transponder. As you can see in the picture on the right, it doesn't just take one client circuit, it takes many different lower speed client ports, wraps them each into their own what are called lower order OTN containers, and then multiplexes those OTN containers together, and then adds the forward error correction, and then creates the wavelength. So it terminates the client, wraps each client individually into an OTN container. Again, it doesn't touch the VLAN or the IP packets, muxes many lower order containers together into one higher order container, and transmit this on the wavelength of your choosing, and that wavelength is now ready to join its other wavelength friends and be multiplexed and carried over distance on the line system. Again, if you have questions, please put them in the Q&A, and somebody will be responding to us. Bruno will be. And then finally, you can imagine if I've got a transponder and then I've got a muxponder that's a little more advanced, shoot, maybe I could just make a full-blown switch out of this, and that is what OTN switching is. OTN switching gives you the ability to groom across many lower speed client ports and many wavelength ports. The reason you would do this is it saves wavelengths, gives you more protection options, and there's actually 5 functions that this performs. You terminate the client optics, and actually it can be a mix of things like OC48, 10 gig, 1 gig, as I'm showing down below. It transparently wraps each client signal into its own OTN container, lower order, doesn't touch the VLANs or the IP packets. Then it allows you, via software, a very simple network management system, to rearrange OTN containers kind of any to any how you want them arranged. Cross-connecting, hairpinning, pass-through, add-drop, whatever you need. And on the high-speed side, it creates these, it creates the wavelengths again, and the wavelengths again join their wavelength friends on the line system as well. So you have transponders, muxponders, and OTN switching capabilities that are all used depending upon your network application. Since we've talked so much about OTN, as we went through the electronic portion here, this is kind of a summary. If you're not familiar with OTN, you can think of it as higher capacity, more flexible, kind of SONET SDH. It's actually time division multiplexed containers, and they have different container rates. For example, in the table you see an ODU0 is a container that's used to carry, for example, a 1 gig E interface. And that ODU container runs at actually 1.25 gigabits. It runs a little faster than a gig. And you have an ODU1 that can carry an OC48 or an STM16. You have this interesting capability called ODU Flex, which is the size of the pipe can vary in multiples of 1.25 gigabit increments. That's ODU Flex, ODU2, ODU3, ODU4, and on up. And of course, we have platforms that do that. We have a small platform called the Apollo 9901. OTN historically has been very, very large pieces of equipment. But like I said, we have big carrier features and small carrier packages. So we actually have a couple very small form factor OTN devices that a number of smaller operators use quite successfully, the Apollo 9901 and the Apollo 9904. And with that, that's kind of the electronic portion of an optical system. We'll talk about the line system and the management system coming up. But before we do, we have a poll question. Lance, you want to take that?
Absolutely, Sam. Thank you. So on your screen, you should see a quick poll question. So what do you see as the biggest drivers for deploying a DWDM or ROADM system? As you can see there, you can select one or multiple choices, capacity to support new services, distance to each new customer's or endpoints, I'm out of fiber, or I'm overbuilding a legacy DWDM ROADM system. So take a minute there. We'll sit back and watch some of the results pour in. And by the way, thank you all for playing the contest there. I do appreciate the activity. We'll have another poll question coming shortly. But Sam, you can see the results pouring in.
I want to know if I won. Was I the first person to type dense wavelength division multiplexing, or did I not win?
You did not win. And even if you did, you would have been stricken from eligibility. So thanks for playing.
Well, good. We're getting an awful lot of responses here, and they're all over the place, which is kind of the way life is. So most people are looking at an optical networking system. Actually, if you want to just share that, Lance, it's kind of interesting. People might want to see it.
Yeah, I can share it, but I have to close it first. So over 60% of you have voted.
Roughly 3/4 of the folks are saying, I just need more capacity. And that is certainly a key driver. About half the folks are also saying, I'm out of fiber. And fiber is really expensive, and some people actually call these systems electronic fiber. So looking like electronic fiber, if you will, to solve that problem. 30% of the people have a distance problem too, because we're expanding, trying to reach new customers, new endpoints. That's a big driver for folks. And there's about 20% of folks that say, I've got a first generation or older generation DWDM or ROADM system out there, and it's out of gas, and I need to overbuild it. So yeah, so thank you for participating. So let's keep going here. We talked about sort of the electronic portion of an optical system, and we go to a lot of trouble to make a wavelength so you can mux wavelengths together on the line system. So now let's talk about the line system in more detail. Line system's job is a couple of things. First of all, to combine many wavelengths together onto a single fiber to achieve capacity without having to build more fiber. That function is called wavelength division multiplexing, or the WDM acronym you hear people say. The second thing a line system does is it manipulates wavelengths. There are some types of first generation line systems, older generation systems. It's very crude and manual on how you have to rearrange the wavelengths. Modern systems allow you to control this very point and click from a network management system. You can add, drop, pass through, or switch a wavelength. You can make things like an optical ADM or what's called a ROADM, which is what most people do. ROADM stands for reconfigurable optical addrop multiplexer. It's a very software-friendly, dynamic piece of equipment. The third thing that a line system does for you is it tames the wild, nasty effects of analog transmission on the fiber to help you achieve distance. In particular, we'll talk about amplification. We'll talk a little bit about dispersion compensation as well. So let's talk about these three functions in the next few slides. The first function, combining wavelengths together using wavelength division multiplexing, or WDM. There's two kinds. Let's start at the bottom. A lot of rural carriers, when they adopted WDM, they kind of started small and used something called CWDM, or coarse WDM, or people will call it coarse wave. And it's sort of it was helpful, but probably a little bit limited in today's world. You could take up to 18 channels, but a lot of systems only supported 8 different channels. The spacing between channels was relatively wide, 2,000 to 500 gigahertz of spacing along the spectrum between the channels. It was really best for things that operate where each channel was kind of 2.5 gig and below. Couldn't really amplify it very far. It helps with capacity, not so much with distance, and it's in decreasing use. It's DWDM, or dense WDM, is where people are going, and in the big carriers, they've been here for a long time. It's just sort of making its way to the rural environments. With DWDM, you can have 128 channels with very tight, instead of 2,500 gigahertz spacing, 37.5 gigahertz spacing on each channel. The channels, depending upon the width, you can actually select that. The channels can be 400 gig in capacity on a single channel or greater. May need wider spacing depending on how far you want to go. We'll talk about some of those trade-offs. With DWDM, boy, you can amplify it. So there's DWDM routes that are in the world that are 10,000 kilometers long. Now, you folks probably don't need to go that far, but going 200 or 300 kilometers, no problem. So it started actually in the long-haul environment, penetrated metro. Now it's drifting down to access and the rural carriers. So DWDM is really where it's at. And let's talk about the grid. I mentioned channel spacing on the last slide. This will help make a little bit more sense of that. Excuse me. Each wavelength consumes a certain amount of spectrum in what's called the 1550 nanometer window, or they're sometimes called the C-band, is a portion of that window. And the early DWDM systems, they sort of had a fixed frequency grid. And these are not like TDM time slots. They're actually frequencies along the electromagnetic spectrum. And the early systems, excuse me, were what are called fixed grid systems, where clearly defined 100 gigahertz boundaries. That's where you had to define the wavelength, and each wavelength that went down the fiber consumed that fixed amount of spectrum. The next advancement in this area was moving to 50 gigahertz fixed grid systems, where the spacing was tighter and you could get even a higher speed channel in a smaller spectral slice. You can get a lot more capacity on the fiber, and you could get up to 88 or 96 channels in what's called the C-band. But where we are today is something called flex grid, where the line system is actually capable of allowing you, the operator, to determine how you want to set up your grid. So the center frequencies are at multiples of 6.25 gigahertz increments, and the width of each channel is n by 12.5 gigahertz. So you can have very tiny channels. The trade-off that we'll talk about coming up, if you have a very tiny channel, you get a lot of channels on your fiber, that's great, but each channel can't go very far. So there's no free lunch, there's some trade-offs. We'll talk about those things. But again, flex grid, that's kind of where the world is heading these days. So let's talk about what determines how much spectrum I need to use for each wavelength. Now, 10 gig, just for a baseline here, 10 gig transponders and muxponders are very simple. 10 gig wavelengths typically use 50 gigahertz or 100 gigahertz spectral grid, and those wavelengths are what are called intensity modulated. So you have an electrical signal coming up to your transponder. At the output of your transponder is a laser, and the electrical signal is used to modulate the light that goes out on that laser. And it uses something called intensity modulation and direct detection at 10 gig. And direct detection is just what it said. If you had the presence of light, that was a 1. If you detected the absence of light, that is a 0. It's pretty simple. That's kind of a baseline. That's where the world has been. Where the world is going now is 100 gig plus transponders and muxponders, and much more flexible, much more powerful, and that's the kind of bandwidth you're really going to need in most cases. And they're much more flexible and many more knobs to turn. So people will call these multi-haul transponders and muxponders, and what they mean by that is you can go a short distance, a medium distance, a long distance, depending upon some of these knobs that you turn. And this is where you can get into trade-offs. You can trade the line rate of the wavelength, whether it's 100 gig or 200 gig or 300 gig. You can trade that off against how much spectrum you use on the fiber and the distance that you need to go. And there's a couple, you're no longer using intensity modulation and direct detection. Now you're using QAM modulation and coherent detection. We'll talk a little bit about those things. And then having the flex grid on the line system allows you to accommodate those different kinds of trade-offs. So let's look at transponders now. These are some of the knobs to turn. So if I'm trying to create a wavelength of a given line rate, let's say 100 gigabit line rate, for example, I've got a couple knobs to turn. I can turn what's called the baud rate knob. And baud rate is, if you're an older person, you may remember your 300 gigabaud modem back before there really was an internet. Baud rate stands for symbols per second, and then modulation is how many bits per symbol. So if you multiply that out, and you've got a couple of what are called polarizations of light that you can send down the fiber at the same time. You take your baud rate times your modulation times two polarizations, and you come up with the line rate in bits per second. So for example, a 100 gigabits per second line, you run that at 34 gigabaud times 2 bits per symbol would be the modulation format times two polarizations. That gets you actually over 100, but that's what allows you to get to 100 gigabit on the line rate side. So baud rate's fairly easy to understand, how many symbols per second. Modulation's a little bit more difficult. You need to think about how many bits per symbol. So with QAM modulation, you can choose QPSK, that's actually 2 bits per symbol. 8 QAM is 3 bits per symbol, 16 QAM is 4 bits per symbol, 32 QAM, and 64 QAM are 5 and 6 bits per symbol respectively. And if it creates sort of a pattern of well, it's a little complicated to explain, but you get this thing called a constellation. So for example, this pattern on the right-hand side is what's called a 64 QAM constellation. You're transmitting 6 bits for every symbol of modulated light that's going downstream. And you can imagine now, if I'm a receiver and I'm trying to receive this constellation, it might get a little difficult for me to detect. The more bits per symbol I have, the more dots I have, it might get a little bit difficult to detect one dot from another dot, and that's where you get into errors. So you can really ramp up the QAM modulation, get more bits per symbol in your channel, but as that comes down the line, it becomes harder to determine, one bit from another, so you can't go as far generally. And that gets you to the world of no free lunch. So if you increase the baud rate, that's a good thing. It improves your transceiver efficiency, or how many bits per device that you're actually sending, but it requires more spectrum, and depending on how many wavelengths you have, you may not have enough, so you got to kind of watch for that. The next thing is you increase the modulation. You improve the spectral efficiency and how many bits per hertz, but you decrease the distance that I mentioned earlier, so it's kind of a trade-off. So if all you've got are fixed baud rate and fixed modulations, you have some limitations. In the service provider world, you sometimes need better knobs and you need more knobs. So one capability that we have on our systems, we give you not just 2 knobs, we give you 3 knobs. 3 is always better than 2. And we let you tune the granularity of those knobs more flexibly. And it's all done with the management system, so you really don't have to know a lot of details here. The important thing is you get the flexibility. So we have something called adaptive baud rate. So we have lots of baud rate choices for you to pick from, not just a couple. And we have this capability called fractional QAM modulation, how many bits per symbol. So you're not just stuck with an integer like 2 or 3 or 4 or 5 bits per symbol. We actually alternate back and forth between a couple different modulation formats to give you sort of like 3.5 bits per symbol or something like this. And that allows you to hit the density you need to hit while achieving the spectral efficiency that you need to hit. And the third knob that we add is something called the line rate combo. Actually, in our equipment, you can take a high bandwidth signal and stick it out just on one channel, or you can take a high bandwidth signal and inverse multiplex it and stick it out actually over 2 channels. So you can pick 100 gig, 2 by 100 gig, 1 by 200 gig, and etc., like shown on the drawing. And this will allow you to meet kind of your unique real-world conditions. The good thing is that we hide a lot of this complexity for you. Okay, so that was kind of complicated. We started to talk about the line system, and we kind of hit the WDM portion of things, and then we talked about how much spectrum you use, for each wavelength. So with that, let's take a little bit of a brain break and do our last poll question for the day. Lance?
All right. Always look forward to these. Sam's famous jokes and punchlines. So please vote for the joke whose punchline you would like to see at the end of today's webinar. Here's our choices. A search engine optimization expert walks into a bar. Second choice, what do you call a boomerang that doesn't work? Third choice, I couldn't figure out why the baseball kept getting larger. And the fourth choice, one windmill asks another, what's your favorite music? So Sam, I'll let you expound on these if you want to.
Yeah, sure. I can't stress this enough. Please vote responsibly. Some of these jokes are really stupid. So, as we say in the U.S., vote early, vote often, but do vote responsibly. Oh, results are pouring in. Okay, I don't know if I can, yeah, okay. I can kind of predict the winner. We've done this before in other webinars, and generally one category of jokes seems to be favored. But anyway, it's anybody's race, neck and neck. If you're passionate about your jokes, be sure to vote. Okay, so we're talking about, let's get back to our problem here. We're talking about line systems. We talked about wavelength division multiplexing and what determines how much spectrum you actually use when you're multiplexing those wavelengths together. Let's talk now a little bit about manipulating the wavelengths that you've created with the spectrum that you wanted them to possess. And we'll get back to the punchline for the joke at the end of the webinar, so you must stick around for that. Manipulating wavelengths, a simple example is point-to-point only. Basically, all the wavelengths that come in at side A, they go out at side B, so you just multiplex many waves onto one fiber. That's not very interesting. People do it. It's kind of niche-y, but you generally need something more than that. So then the next thing is this concept called fixed optical addrop multiplexers, or FOADMs. You'll see an acronym of that. If you have deployed some kind of WDM, you might have deployed a FOADM. Lots of rural providers would do that. It's kind of it's effective, but it's kind of a quick and dirty way to deal with smaller amounts of capacity. The hardware is very inexpensive. The problem is it requires a truck roll and manual configuration. If you're dropping a wavelength out at, say, the red wavelength comes out at site B, only runs A to B, you got to send somebody out there to do something to make that happen. But with a ROADM, a reconfigurable, sorry, there's a typo there, it's a reconfigurable optical addrop multiplexer, it's automated. So it automates the wavelength manipulation to help you create larger networks that you can manage and rearrange and resize traffic on. There's actually 4 different kinds. There's what's called static ROADM. See, the world's just too darn complicated. There's something called a static ROADM, but I'll explain this. Colorless ROADM, colorless directionless, or colorless directionless contentionless. And generally, as you go from static to colorless to CD to CDC, you get more functionality, but it costs a little more. So there's trade-offs, and we see people deploying different kinds of ROADMs for different reasons, and actually that's something we can help you with if you want that kind of help. Or our partners can help you with that as well. So brute force networking, this is kind of just point-to-point multiplexing and demultiplexing. I got 4 sites A, B, C, and D, and I got some wavelengths, a blue, a red, and a gray one there. And the way to do this is I've got WDM multiplexers and demultiplexers. Those are those blue trapezoids. And I just multiplex and demultiplex all my waves at every site. This is kind of a manually done, this is basically like chaining a bunch of point-to-point systems together, or a manually done OADM system. It's cheap, but I have to do a lot of manual stuff, and I get very heavy loss at sites B and C for any wavelengths that need to go through those sites. Every time I go through a mux demux, there's loss. I don't like loss. Loss limits my distance. So with a little better improvement, there was something called these fixed OADM units, or the FOADM that we talked about earlier. In this case, the FOADMs will allow you, like at site B and site C, they'll allow you to add and drop predetermined channels at those intermediate sites, and it will pass the remaining channels through without demultiplexing. So it's simpler. You get lower loss for the stuff that goes through, but you still kind of have to know ahead of time which wavelengths I'm going to want to drop at B and which wavelengths I'm going to drop at C, and there's still some manual operations involved, and it's less flexible. But a lot of people have done that. But moving into ROADMs, that's where really the world is going. You use a device, and it's shown there in Site B and Site C is that kind of pink thing with the squiggles in it. And that's called a wavelength selective switch, and use those devices at each ROADM node. And now I can just send a software command, and the WSS, the wavelength selective switch device, will either add, drop, or pass through wavelengths based on that software command. WSS devices offer many other benefits other than just manipulating wavelengths. They dynamically balance the power that comes in between all wavelengths that are sharing a fiber. Remember, the line system doesn't deal with bits. It just understands color, and it understands the wavelengths of light, and it understands the power in each wavelength. The WSS understands the power that's contained in each wavelength of light. So it's truly an analog world. So you get to dynamically balance the power between all waves sharing a fiber. You can dynamically control the input power of incoming waves at sites A and D. I can automate these multi-degree sites. This is just a simple linear chain. But site B and site C, I could have a north, a south, an east, a west, a northeast, a southeast, and I can shoot traffic any different ways across the compass there. And I can actually reconfigure wavelength paths during a maintenance window. Like if I'm going to do some work on a cable, what a lot of folks do is they'll go into their ROADM system and they'll just move the wavelengths around the other side of that network and get the traffic away from where they're going to do planned cable maintenance. And that way they make sure they don't have some kind of an outage. And like I said earlier, we do have large carrier features and small carrier packages. When I started working with ROADMs a few years ago, ROADMs were giant systems. They take like a third of a rack, and they cost like they take a third of a rack. But now they're very, very small. So we have a platform called the Apollo 9603. It's just a couple of rack units. And we put in this thing called a micro ROADM, and I'll show you here, my handy prop. This is the size of that micro ROADM blade, and that micro ROADM blade actually has the WSS device right on the blade, and those little pink those little green boxes right on it, those are actually amplifiers that you can plug in like on CFP2 form factor amps. So the cost and size of these WSS devices come down dramatically. This is the smallest thing I'm aware of on the market and a great fit for a lot of rural operators. So let's talk now about the different kinds of ROADMs that exist. And this may be a little hairy for folks, but we'll talk about it anyway because you'll see these terms. You'll hear people talk about a CD ROADM or a CDC ROADM, or do you have a static ROADM? Static doesn't mean bad, they're just all different. So with a static ROADM, let's start on the far left. That's the simplest thing. You can see I've got a router there in blue. And that router has its client optic at 1310 nanometers, the gray optic on the client, going into the client side of a transponder. And then they're showing these kind of three black lines that connect the transponder to something called the addrop or collector portion of the line system. In a static ROADM, when I make that jumper between the transponder and the addrop collector on the line system, I am now, that's my port, and I'm tying that port to a direction, either east or west, and I'm tying that to a color or a wavelength number. So for example, that third port there where the arrow is pointing, the port on the right, that in my example here, that's connected to the direction east, and it's wavelength number 1 or something like that. So it's static. On the through side, it's all dynamic. I can rearrange wavelengths like I talked about earlier, just the drop side toward the transponders is fixed. Colorless ROADM gives you a little bit more flexibility. And again, I've got my router connected with a gray optic to the client side of a transponder. Then on the line system side of the transponder, I've got three little lines there. And now those ports, they're tied to a direction, say east, but I can pick any color for those 3 ports that I want to pick. I can call them wavelength 1, wavelength 2, wavelength 3. The color is no longer bound to the port, so it's more software friendly, more flexible. Colorless directionless takes things to the next level. I still have these ports between my transponder and my addrop collector, but now the port is not tied to any direction at all. It's not tied to any color. That should say port is not tied to. The port is not tied to any direction. The port is not tied to any color. And only one, the limitation is only one drop port can occupy a certain color. So only one of my drop ports can be wavelength 1. I can't have 2 drop ports that are wavelength 1. The reason you might want that, say at this site here I've got two directions, west and east, I might want to have two different pieces of traffic, two different clients. One of them be wavelength 1 going west and another one being wavelength 1 going east. And with a colorless directionless ROADM, you can't do that. You can only use wavelength 1 one time on the drop side. The most sophisticated kind of ROADM is called a colorless directionless contentionless ROADM. And again, I got my ports between the transponder and the addrop collector. And the port is not tied to a direction. The port is not tied to a color. And now many ports can occupy a single color on the drop side, so that eliminates something called drop side contention. So in very large network, very large service providers, they go with CDC because their big deal is automation. What we see in the rural operator space is more of a mix. Generally, people will go with a static or a colorless directionless model because it's a little less costly, if that makes sense. The ROADM system that I showed you here, this is kind of with a pluggable micro ROADM. That's kind of the ROADM line side in these pictures here. And then we offer you a choice of addrop collectors for how you want to trade off flexibility for cost. Okay? Whew. That was a lot. Glad you're hanging with me this morning. Let's press on. Finally, so we talked about, the three things a line system does: wavelength division, multiplexing. It manipulates wavelengths. We showed you the different options for manipulating wavelengths. And the third thing was overcoming the wild, nasty effects of analog transmission. It's analog. What could possibly go wrong, right? Lots of things. The first thing that goes wrong is, probably the thing you need to think about the most is optical attenuation or loss. These wavelengths, when they're shooting down that really clear piece of glass fiber, they do lose power as they travel down the fiber. And when they lose a sufficient amount of power, excuse me, the receiver can no longer determine a 1 from a 0. And a parameter known as the optical signal-to-noise ratio becomes too low for the receiver to determine, and you'll get bit errors, is what happens. Sorry about that. And the way you fix that with an optical amplifier. We'll talk about that. The second thing that can go wrong, and this is mostly like a 10G thing, for 100 gig and above, for coherent systems, dispersion is not so much of a problem. Basically what that is pulses of light. Think about 10 gig, that was a intensity modulated direct detected system. Those pulses of light, they actually spread out as they travel down the fiber, so the receiver can't tell one pulse from another. You fix that with something called dispersion compensation. Third thing is something wild and hairy called nonlinear effects, where certain wavelengths, if they have too much power, they can actually trample on other wavelengths using things like four-wave mixing or Rayleigh scattering, other types of effects. You can overcome this with good optical network design, or the fiber itself is damaged or connector is broken. You fix this with armed guards and eternal vigilance, or you can react quickly and proactively with an automated network of TDR. So let's talk about attenuation and loss and how that reduces optical power. You get losses from the fiber itself. There is some loss from WSS devices, and there is some loss from mux, demux, and filters. Amplifiers, which you'll hear called EDFAs, EDFA stands for erbium doped fiber amplifier, that'll boost the power. The magic here, and why WDM economics works so well, that amplifier will boost the power of every wave or all the waves on the fiber at once with one device without terminating any of them. That's the economic power of WDM and what allows us to do Zoom calls essentially for free, or WebEx calls. That's the key to the economics. Again, the amps don't understand bits. The amps actually don't even understand wavelengths. All the amps understand is power, and they'll take small power in and big power out. So there's booster amps that go on the output side of a line system. There's an inline amp that goes between locations. That's necessary sometimes, and there's a preamp, which is on the receiver side. Generally speaking, you can get by with just a post amp or booster and a preamp, but for very long distance routes, you might need an inline amp. The bad thing is no free lunch. Amps create noise. Only so many amplifiers can be in the chain before the signal to noise ratio is ruined and the receiver can no longer figure out what's going on. More no free lunch in the analog world. An amplifier's gain, the gain is sort of power out divided by power in. Power out's always higher. That amplifier gain changes. It's not just one number. It actually changes with the input power, and it changes with the frequency of each wavelength. Okay, that's a bad thing, but it's physics and you can't get around it. And the second thing is the amplifier noise that gets generated also changes with the input power and the frequency of each wavelength. The good thing is we have software to help you with that. We have software called Cleverly Network Planner. It helps you plan and design your networks, and you can run it offline, and then you synchronize it with the production network, and you can make your optical design based upon the traffic demands, and you can pick the type of amplifier that you're going to need, and you can test all these trade-offs between line rate and spectral width and distance. You can test whether your wavelength will reach the distance without needing to be regenerated, and that's very expensive. You don't want that. So basically with Network Planner, you can kind of figure that all out in software and design your network how it needs to be done. Let's keep moving here, and that's amplification. That's mostly what you're going to need to worry about, but dispersion is something you should understand because people will talk about it, and if you're running any 10G, you need to think about this. Dispersion is when pulses spread down the fiber. It applies to 10 gig waves and below. Basically, this is just physics. The leading edge of the pulse will travel faster, actually travels faster down the fiber than the trailing edge. Pulses bleed together. It causes bit errors, largely eliminated in coherent systems. You fix it with something called dispersion compensating fiber, DCF. You put the DCF into a plug-in unit called a dispersion compensation module. And that dispersion compensating fiber is special fiber, and it sits right in the data path with your outside plant fiber. You deploy it at the receiving end, and that special fiber is, the glass is chemically doped to actually undo the pulse spreading that is done by your outside plant fiber. The bad thing is that causes loss. So if you want to build a network that's a mix of 10 gig and 100 gig waves, some people do that, but you're going to suffer a little bit of compromise because if you're using DCMs to satisfy dispersion on the 10 gig wavelengths, that will actually worsen the performance of the greater than 100 gig coherent wavelengths that you may want to use later. So generally speaking, it's a better long-term bet to go with 100 gig and above, and this is one of the reasons why. So let's keep going here. One of the things you need to worry about is not just physics, but you need to worry about small animals that bite your cables and people with shotguns who are bored. So you're probably familiar with an optical time domain reflectometer, and you may be familiar with that as a handheld test set that you drive around to different locations to help you figure out where fiber failure has occurred. A network OTDR is a nice piece of technology that is an OTDR, but it's deployed right in your existing fiber plant. And the beautiful thing about this is you can deploy this right in your fiber plant, and you deploy it in service alongside any other kind of equipment that you may have on that fiber, SONET equipment, Ethernet equipment, whatever. Even if it's something that's not from us, it's from another vendor, you can deploy this solution right alongside that. And what that network OTDR will do, you control it with software remotely, and it will scan automatically multiple fibers at once for defects or cuts, and it'll raise alarms if the fiber's been cut. It'll tell you where it's been cut to within meters, and so it dramatically reduces the repair time, dramatically reduces your OpEx cost, actually even allows you to anticipate failures because you can see things degrade over time. So this is a very powerful function for people who are doing maybe building a larger network than they've had before, and their operational staff is small. Very cost effective, and you get a great payback in a hurry with this kind of solution. So let's talk just a little bit then about some technology design and deployment considerations. There are things that you just need to think about when you're building these types of networks. Are you going to have things that impact your distance requirements? Well, I need to add sites or grow my network geographically. That's something you have to take into consideration when you're doing your design. You've got things that impact the capacity that your network is going to carry. Can I get away with a 10 gig wave, or do I really need to go with 100 and above? In the coherent world, will I be rolling out higher speed residential broadband? Will I be doing mobile backhaul for 5G? If you're a rural operator, You may be tempted to think that 5G isn't going to impact your life much, and actually it will. There's lots of applications out there in rural environments that can benefit from 5G, and the mobile operators who are deploying those radios, they're going to need backhaul and they're going to need it from you. So that's a nice revenue opportunity for you, even if you're not in the mobile game and even if you are a rural provider. That's going to impact the capacity on this network. It's important to be thinking ahead. And finally, things that impact your operations. Am I reducing my operational staff? Am I trying to cover a larger geographical footprint? And then finally, what are some things that can help me build out rural networks, smaller optical networks? I'll just list a few things. We've touched on some of these earlier. First of all, our optical platforms at Ribbon are branded as Apollo platforms, which you probably heard me talk about earlier. We also have Ethernet and IP platforms that are branded as Neptune. So lots of people, what they do is they use a Neptune platform to aggregate traffic in from like GPON systems or fixed wireless access systems. But they might have a little bit of, you need that Ethernet and IP aggregation, but you might have a little bit of a distance problem. And if your network doesn't justify a full ROADM, for example, we actually have kind of wafer thin amplifiers and WDM pieces of that line system that you could put right into the Neptune platform. So it's a very cost-effective addition if you don't need a lot of capacity. But as we saw in the poll question, capacity is a big deal for folks, so we have the Apollo Micro ROADM. It really gives you a lot of future-proofing capabilities. You get all the automation benefits of a ROADM, and it's really in what I think is, to my knowledge, is the industry's smallest package. And Elizabeth sells everything by the pound, so that means it's cheap. So we also have 9901, 9904 OTN appliances, also very small form factor for grooming of channels before you create the wavelength, if you need something like that. Our network management system is a product called LightSoft, and that is a very elegant system that a lot of our customers like because it manages both the optical layer and any Ethernet or IP equipment that needs to go along with that, all from a single pane of glass, and it runs that network planner software for optical network design that we talked about earlier. And finally, we have something called Light Pulse Network OTDR to automatically find degradations in fiber before failures occur, or to identify the location of failures to within minutes instantaneously. And actually, we have customers where that's the initial thing that they've used from us. They have maybe an embedded SONET network or an Ethernet network or something like this, but they're having problems with their fiber plant. They say, boy, let me embrace this network OTDR and I'll use that, and I'll worry about upgrading my network later. So that was a lot of information. Optical networking demystified. We covered a lot of things. Do we have any Q&A, Lance, that people want to go over?
Hey, Sam. Yeah, we have a few, and Bruno, I don't know if you're on and want to address any of these specifically. We've had several that we could do verbally. Let's see here. Yeah, while we're looking at these, look at the screen there. Sam has just put some contact information, so in case you want to reach out directly to Elizabeth, Sam, or Bruno, you have their contact information right there. But let's take a look. So one question came in. It says, and maybe you covered some of this, Sam, but the question was about dispersion. How far can I go without dispersion?
So if I'm running at 10 gig, dispersion happens all the time. So it depends upon the dispersion tolerance of the receiver. So you might, that's really what it depends upon. So it may be, 80 kilometers or something like that before you start being limited by dispersion. You may be able to go farther in certain situations, but generally you're going to have some sort of dispersion compensating fiber to help you undo that dispersion.
Okay, and here's another. I'm just going to read it verbatim so we can get the full context of the question. But while the cost of DWDM seems to be coming down a great deal, allowing for rural communities to look more at this solution, what type of layer 3 solutions, or from a load balancing perspective, what type of options are available? And also, what are the failover times in a DWDM network?
Okay, let's take the failover times first. It depends on what layer you're protecting. You can actually protect at the wavelength layer itself. And Bruno, jump in and correct me if I misspeak here, but you can actually take a wavelength and kind of send it around both ways around the ring and kind of do like a pass switching protection on the wavelength. That takes a couple of seconds to do the switchover usually. If you're using some sort of OTN capability, we have those OTN muxponders and switches and transponders, and you make a couple different OTN containers, you can protect OTN containers, and that is a 50 millisecond thing as well. On the routing side, I don't know, Bruno, is that something you want to touch on real quick?
Right. Yeah, can you guys hear me?
Yeah.
Okay, so first of all, you're right on the optical side. The lower the layer that you do the protection, the faster the protection is, because you don't have to wait for propagation of protocols to figure out the new path. It's already predefined. Also, you know, the loss of light can actually generate the switch much faster than waiting for the, you know, control messages or BFD messages to issue the switch. So you can do switching, you know, below milliseconds. I mean, you can actually go to microseconds if it was designed right. Now, regarding the layer 3 function, that was out of this concept of this WebEx, but at layer 3, there's multiple ways to provide functions like load balancing using, being able to use load balancing by providing multiple connections. You can use lag for having both protection and load balancing. That would be under the Neptune line. We have the ability to let the system figure out if they want to do load balancing on the multiple connection, or they want to do protection on the multiple connection, or a combination of both. And you can actually static define, and again, that's the relationship between layer 2 and layer 3, and for that you would need something like a multi-layer orchestration in order to figure out how you want to split the traffic on the different layer 0, layer 1 connectivity trace that you're going to have. So if you have multiple lambdas, you can define that up to a specific amount goes on each lambda, and this way you can provide different load balancing for each one of those lambdas, and the selection is going to be done at the layer 3 or even at the application layer if needed. Hopefully that answers the question.
Okay, thanks, Bruno. There was one other that came through just now. How can we identify the non-linearity in the network?
Okay, good, thanks. And I didn't speak to that very much, but let me kind of speak to that briefly. Non-linearities occur when you're trying to launch too much power into the network. It might be tempting to say, boy, I need to go a long distance, therefore I'm just going to really blast this wavelength through, and that'll get the long distance problem is that causes problems with other wavelengths. And the way we solve that is with the optical network design software. It will make sure that, and the WSS will make sure the power levels don't get too high. Where you need to think about this is if you're deploying a line system, we talked about those 3 pieces of an optical networking solution. If you're deploying a line system from one vendor and then you want to shove a transponder under it from another vendor, sometimes the transponder vendor may launch a higher power because their line system can tolerate that, but the line system you're using may not be able to tolerate that. So that's the kind of thing where you have to watch out. But if you're not doing that and you're deploying generally things from a single vendor, the network design will take care of those nonlinearity issues for you. Okay, and with that, we're almost on the end of time. Should we do the joke?
Absolutely. So kind of as expected, the winning joke was a search engine optimization expert walks into a bar.
Actually, we do have a couple of late questions. I'm sorry to do this to folks. What are the challenges in transporting 400 gig, 800 gig wavelengths in optical networks? That's a really good question. Let me just see if I can speak to that briefly. There's a couple of challenges. Generally speaking, a 400 gig or an 800 gig line rate wavelength will need to occupy more spectral width than a 100 gigabit wavelength would. So it's not necessarily a problem. unless you've got a line system that you're already using and that thing is 50 gigahertz spaced and fixed grid. If that system is 50 gigahertz spaced, you're going to be very limited in distance for your 400 gig or 800 gig circuit to travel down that fiber. So this is where that third knob that we have, the ability to have what we call line rate combo. So in our solution, you can actually take a 400 gig, instead of doing a 400 gig wave, you could do two 200 gig waves, inverse multiplex your client traffic across both of those, and run each 200 gig wave in a 50 gigahertz slice on your fixed grid line system. So stuff like that is kind of what you need to think about. 800 gig, it's fine if you have a flex grid line system, no problem. It'll just go a shorter distance and you need to be aware of that trade-off. There's a lot of what I would call sort of hype in the market right now around 800 gig. You know, that's the thing you need, that's the thing you need. It's not necessarily the thing you need. It's the thing some people need. Generally speaking, the cloud and content people can benefit from 800 gig because they're not transporting that signal very darn far, and that's a good fit for them. But for rural folks, 200 gig, 300 gig, 400 gig, that's plenty. And also you requested, can we have another session for protection like ASON? Yes, we could. And case studies for applications on utility market, power and gas in the future. Yeah, we have lots of case studies around that. We've done a lot of work for critical infrastructure folks. We can talk about that in the future as well. So sorry about that diversion, Lance. The joke, the winning joke was,
yeah, a search engine optimization expert walks into a bar.
Oh, this one's terrible. There's going to be a severe amount of buyer's remorse here. Maybe I should wait till more people drop off. Okay, a search engine optimization expert walks into a bar. Bars, public house, pub, tavern, beer, alcohol, wine, liquor, whiskey.
I think I get it.
Yeah. That's terrible. You know, search engine optimization, you get all these related terms. Okay.
Yeah, nice.
I'm sorry, that was, most people like the bar jokes, but that was not good. Let's do number two. Number two was not far behind, and it's probably funnier. One windmill asks another, what's your favorite music? The windmill looks back and says, I'm a big metal fan.
Agreed. Much better joke. I like that one.
I like them, Sam. Thank you very much.
Yeah, I got some thoughts there first this time, but you know.
You're getting some terrible jokes in the comments section there, Sam.
Well, I need more material, so this is just fine.
Yeah, thank you.
Hey, well, thank everyone, and I appreciate everyone's participation with the poll questions, with the jokes, with the general questions that came in. Thank you for suggesting additional webinars as well. We do appreciate that. We had somebody ask about doing one on protection schemes on optical networks. So perhaps we'll put some thought around that and deliver that sometime early next year. So appreciate those comments. We appreciate your questions. We'll get, if we didn't answer your question live or via the chat, rest assured you'll be getting an answer at some point, hopefully by the end of today. We'll respond back to you with some more questions, or I'm sorry, some more answers to your questions. Later this afternoon, you'll get an email from me with a link to the replay, as well as a link to the slides, so be on the lookout for that. And as I always like to mention, you have the contacts there on your screen you can reach out to. You can obviously find more information at ribboncommunications.com and find plenty of ways to contact us there. So before we part ways, Sam, Elizabeth, or Bruno, any last comments before we close out today?
Yep, thank you all for joining. Greatly appreciate it. And as Lance just mentioned, we'll start working on the next one. Sounds like you had a good presentation today, Sam. So even with your jokes, people want to hear from you again. So thank you for presenting. Thanks everybody for the comments, and we'll start working on the next one. Appreciate it.
Okay. Take care, guys.
Thanks.
Thanks so much. Bye-bye.